So welcome back, learners. So in the previous session we were discussing about the design for shear reinforcement, and in which I told you that how to calculate the nominal shear stress, how to get the value of design shear strength of concrete, how we compare these two, and how we make decision that whether the minimum shear reinforcement is required or the shear reinforcement for the design requirement is to be provided. So just to recall, if tau v is less than tau c, then minimum shear reinforcement will be provided. If tau v is greater than tau c, then this shear reinforcement will be designed. And of course, the another comparison between the tau v and maximum shear stress was also there, and if tau v is greater than tau c max, then we have to redesign the section. And I told you that what are the methods of providing the shear reinforcement and what is the value of how to calculate the shearing resistance for these different arrangement of shear reinforcement. Now let's see, based on that knowledge, let's solve one example problem regarding the design of shear reinforcement. Here an example problem is given here, which says that design a beam for shear reinforcement having a cross section of B by D as 250 by 500. It is reinforced with 4 bars of 20 mm diameter. The factored shear force is given as 130 kN, and it says that use M15 concrete and steel as Fe250, and it says us to that provide vertical stirrups only as shear reinforcement. So the shear reinforcement arrangement is also specified here, that vertical stirrups are to be provided. Now how to proceed? As I told you in the previous session, first of all we will calculate the nominal shear stress, and for calculating the nominal shear stress, the information that we should have with us is shear force, design shear force, and the section size, means the width of the section and the effective depth of the section. So B and D. So in the problem itself, Vu is given, factored shear force as 130 kN. Size also given, B into capital D. D is here is the overall depth, but we need the effective depth. So we have to first calculate the effective depth of the section, and for that we have to assume the clear cover. So let's assume that clear cover is 35 mm. So with this assumption, we can calculate the effective depth of the beam as 500, means the total depth, minus cover, clear cover, minus half the dia of the bar, reinforcing bar. So that way we get it effective depth as 455 mm. So using this value of 455 mm, we can calculate the tau v as Vu by Bd. Here this comes out to be 1.143 MPa. This value should 455 instead of 450. Now we should find from the code the TOIC max, maximum shear stress for the concrete. As you know, the concrete grade given here is M15. So for M15, from code you will find that TOIC max is 2.5 MPa. Now for TOIC, for getting the value of TOIC, we need the two information. One is grade of concrete, that we know, M15 is there, and second is amount of tensile reinforcement, that is percentage tensile reinforcement. Because with these two informations we can get the value of TOIC from the table given in the code. So percentage of reinforcement you can calculate as AST by BD into 100, whereas AST is the area of tensile steel, and in the problem it was given to us 4 bars are there of 20 mm. So you can calculate the area of these 4 bars as 4 into pi by 4 into d square. D means the diameter, here it is given as 20 mm. So this area AST comes out to be 1256.64. So putting these values here, we get the percentage of tensile reinforcement as 1.1%. Here, for this M15 grade of concrete and 1.1 percentage of tensile reinforcement, we have to find the value of TOIC. In code, when you do not find the value directly corresponding to a particular value of percentage tensile reinforcement, then you have to interpolate to get the value of TOIC. Here also this interpolation is done because the information is available for 1% and 1.25%. So for the 1.1% we can calculate by interpolating this value like this, and this TOIC is calculated as 0.616 MPa. Now we will compare these values, that is nominal shear stress, TOIC and the TOIC max. Here you see that our nominal shear stress is 1.143 TOIV. TOIC max is 2.5. So if we compare these two values, then one thing is certain, that we need not to redesign because TOIV is less than TOIC max. Now we have to compare the TOIV and TOIC. TOIC is 0.616 and TOIV is 1.143. So here we find that TOIV is greater than TOIC. Means we have to design the shear reinforcement, and as I told you in the previous session that we have to design the shear reinforcement for a value of shear force that is over and above of VC. Means this is VU as design shear force will be here now, VU minus VC. VU, that is the factored shear force, 130 into 1000, and VC we can calculate from tau C into B into D by multiplying tau C by the effective cross-sectional area. So we get the value as 59930 Newton or 59.93 kilonewton. This value we get from this formula. Now let's decide that we provide 8 mm diameter 2-legged vertical stirrups, because this suggestion is given itself in the example problem that we have to provide the vertical stirrups only. So we have to take a decision here to decide the diameter of the bar, these vertical stirrups, and we are deciding here that we are going to provide 8 mm bars and 2-leg vertical stirrups of these 8 mm bars. So with this much information we can calculate the area of this shear reinforcement. It is 2-legged vertical strips, so in the cross section 2 legs will be coming into the picture, means 2 cross sections of this 8 mm diameter will come into the picture. So area ASV you can calculate for 2 bars of 8 mm diameter, and as you see here ASV equal to 2 into pi by 4 into 8 square. This area comes out to be 100.53 mm square. Now to design the shear reinforcement, here the decision yet to be made is regarding the spacing, because area of stirrups we have calculated. Now the important decision is the spacing of these stirrups, and as you know, for the case when the vertical stirrups are only provided, you can use this formula that I earlier told you, that ASV, earlier it was in the form of ASV, now I have rearranged it in the form of SV, because now ASV is known to us. Only unknown in this formula is SV. So for such a situation we can calculate SV, because Fy is known, ASV is known, D is known, VUS is known. So from these, putting these values in this formula, we can calculate the spacing of these vertical stirrups, and we reach or we calculate this value, and it comes out to be 166 mm. So our spacing of the vertical strips as calculated comes out to be 166 mm. Now as you know, for this much spacing we have to check with our codal provisions also, because maximum spacing is defined in the code and this spacing should not cross that limit. So that spacing, that maximum spacing or limitations in the code was that this should not be more than 0.75 D or 450 mm, whichever is less. So here we see that 0.75 D means 0.75 into effective depth, and this value comes out to be 341.25, which is much higher than our value provided, spacing provided, and also it is our spacing that we are going to provide is less than the maximum value of 450 mm that is specified in the code. Means this value that we are providing is safer side. We can provide it very well. Now code also says that, so with this much spacing, we can get the value of the shear reinforcement provided. But code also specifies that minimum shear reinforcement should also be there. That limit should also be met with. Then here, from that point of view, means limiting shear reinforcement means that total shear reinforcement provided by us should be greater than, at least equal or greater than, the minimum shear reinforcement. So from that angle or from that point of view of the minimum shear reinforcement, we have to compare this spacing also. So here, from that point of view, that maximum spacing SV max required for minimum shear reinforcement, that is 0.87 Fy into ASV upon 0.4 B. And for this case, if we put these values, this comes out to be 218.65. Means spacing should not be greater than this. And as you see, we have provided, or we are proposing to provide, as 166 mm. So our design is safe. So the decision is that we will provide 8 mm 2-lagged vertical stairs at a spacing of 166 mm. So this is the solution of this particular problem when we are asked to design the shear reinforcement in the form of a vertical stairs. So this was one problem. Some more problems are given in your blog, so you go through those problems. Now we will move to another part, that is design for torsion. So till now we have discussed design for shear. So another aspect that we have to take care, or that we generally face in practical problems, as I told you in the start of the previous session, is torsion also. So let's move to the design of torsion. Now first of all, the question comes to our mind that what is torsion? As you know, torsion is also known by some other names as torsional moment, torque, twist. So these are the synonymous name to this torsion. Now, what is this torsion or torsional moment? Whenever there is equal and opposite moments applied at both ends of an structural element about its longitudinal axis, then this torsional moment or twist or torque or torsion is there in the member. And if you remember your study of the strength of material course, then in that particular course it was told to you that if there is a shaft, of course a circular shaft we are talking about, if there is a circular shaft and on this shaft, as shown here in this picture, on this shaft, this torsional moment T in equal and opposite directions of the two ends of this circular shaft are acting, then under the action of this torque or torsional movement or twist, what happens that some of the fibers of this element of this shaft changes its position. As you see in this picture, from this position, this particular element has, under the effect of twist, reached to this position. Means there is a twist of fiber or element by an angle theta, and here this angle theta is called as angle of twist. Now T is the applied torsion or torsional movement. Now if for this cross section, if J is the polar moment of inertia, this you know, you have studied in your earlier course, and G is the modulus of rigidity, and theta is the angle of twist, and if L is the length of this circular shaft, then for this case we can write a relationship between these different elements as T by J equal to tau by R equal to G theta by L. T you know torsional moment or torque, J you know polar moment of inertia of the cross section, tau is the torsional stress, of course the shear stress, torsional shear stress at radius R, because this stress varies with the distance of that fiber or that point from the center of the section. So this depends upon this distance R. So this is torsional shear stress at radius R from the center. And G you know modulus of rigidity, theta you know angle of twist, L you know the length of shaft. So for this circular shaft we can write this expression, we can write this correlation between these different elements, different terms. And as you see, this is the torsional stress distribution along the section, this circular section. At a section passing through the center, this is torsional stress is 0. At the outermost two places of this section, up and down, it is tau max, and at any distance r, this is tau. So this is the expression that we generally come across in case of theory of structures or mechanics. Now let's study about the torsional rigidity. Torsional rigidity is the amount of torsion required for unit deformation or angle of twist. Means it is torsion per unit deformation or torsion per unit angle of twist, and it is expressed as T by theta can be equated to G J by L. These G, J and L you know. Now this is about the circular shaft, but what happens in the practical situations? Our RC members are mostly either of rectangular shape or of T shape or of L shape. These are very rare that they are in the circular shape. So what happens that in practice, this evaluation of torsional rigidity, shear stress, etc., these things, these we take based on the experimental results rather than the analysis, rather than this elastic analysis. Because for these shapes, for this rectangular shape, T shape, L shape, this theory of elasticity, determination of this torsional rigidity, shear stress and these other parameters, this is very difficult, very cumbersome to calculate based on the theory of elasticity. So what we do, we go for the experimental results. Some prototypes are tested for the various shapes, and based on the experimental results we calculate this torsional rigidity and shear stress distribution that way. So the meaning is that in practical situations this our theory of elasticity is not of much help, and we depend upon the experimental result to get these values. Now, what is there that bring in the torsion into the picture in the design and construction of the structural members? Torsion in a flexural member can develop only when the transverse loading on the structural member is not lying in the vertical plane passing through its axis or its shear center. What is the meaning of it? Let's see. If this is the beam, then this vertical plane passing through the center means if a plane is passing through the center of the line of this axis, if the load is acting in this vertical plane passing through the center of this beam, then in that case there will not be any torsion, torque or twist. But if we add some element here or here across, and on this element if load is applied here, now the vertical plane having the load and the vertical plane passing through the axis of the central axis of the beam, these two are different. And here what is the effect? That this load is acting at a little distance from this beam. Then what will happen? That it will generate a torsional moment that will act on this beam. It will try to twist now. It will try to twist. So that way torsional moment or twist comes into the structural members. So this is the condition. Means when the applied load is not passing through the vertical plane, or that it is not lying in the vertical plane of the structural member, then in that case torsion comes into the picture in case of the flexural members. So this is the condition when torsion comes into the picture in case of flexural members. In practice, reinforcement for torsion are not designed separately. It is very important statement here that we are not going to design the reinforcement for torsion separately. Then the question comes, how then we take care of this? This torsional resistance of a member may be enhanced, means this can be taken care of by doing two things. One is by increasing the strength of concrete. Means increased strength of concrete means increased resistance to torsion. And second remedy is by increasing the amount of longitudinal as well as transverse reinforcement over and above that is required for bending and shear. Because we are providing already the longitudinal reinforcement and the transverse reinforcement for bending and shear. So if we increase that amount of this longitudinal reinforcement and torsional transverse reinforcement, then this torsional resistance of a structural member can be enhanced. So these are the two remedies. But generally we go for the second remedy. Let's see how we move to take care of this torsion. So the reinforcement for the torsion can be designed for the two different cases. Here we are designing our reinforcement, we are calculating reinforcement from two point of view, that is for bending and another is for shear. So here the strategy is that we do not go separately for calculating or designing the reinforcement for twist or torsional aspect. We are adding the requirement, we are adding some additional reinforcement to the bending requirement as well as the shear requirement. So let us take the first case here as shear. How we modify our shear requirement reinforcement to take care of this torsional reinforcement. So for this we calculate or we find out the equivalent shear. What is this equivalent shear and how we calculate it? This effect of torsion is combined with shear, and an increased value of shear is called as equivalent shear. Means we increase the value of shear force, we increase the value of shear force by calculating, by using some formula, and this increased value is called as the equivalent shear, because shear was already coming into the structural member and we are adding up some more shear, so that we are finally calling it as equivalent shear. This VE equal to equivalent shear is equal to VU, that shear force originally, plus 1.6 TU by B. This is the contribution or this is the addition which we are taking to take care of the torsional moment or torsion. This 1.6 into TU by B. Here TU, you know, it is torsional moment and B is the width of the member. Now, as we told you that in case of shear, design for shear reinforcement, there were different cases. Similarly here also we will deal this situation also similar to the earlier case. Earlier we were comparing the nominal shear stress that we calculating from the shear force, design shear force. Here we will be comparing the equivalent shear force. Instead of simple VU, we will be comparing the shear strength of a section with the equivalent shear. So here, similar to the earlier cases, 3 cases are given here. If equivalent shear VE is less than or equal to VC, then in that case, as we did in our earlier case, we will provide here also nominal shear reinforcement. And those expressions we will see how we should move forward. Second case is when this value of equivalent shear VE is more than the value of tau C max into BD, means maximum shear stress into the effective area. Then similar to the previous case, here also we will go for redesigning of the section, because equivalent shear is crossing the maximum shearing taking capacity of the section. So for such case, the only remedy is to redesign the section and at least bring this level of VE to equal to the VC. The third case that we see is when VC is less than VE and VE is less than tau C max by BD. Means in this case, this second situation is not there, but VE is greater than VC. So in this we have seen such case in earlier provision also, in earlier case when we discussing about the design of shear reinforcement, and similarly here also we will go for the design of shear reinforcement. Now in this case, when torsional moment is coming into the picture to the structural member, then code says that only 2-legged closed stirrups enclosing the corner longitudinal bars should be provided to resist equivalent shear force having a cross-sectional area of ASV equal to TU into SV upon B1 D1 into 0.87 Fy plus VU SV upon 2.5 D1 into 0.87 Fy. Means this is the area of the cross-sectional area of the stirrups. That way we will calculate here. That is the requirement, and the condition is that only 2-legged closed stirrups, and that too with the rider that it should enclose the corner longitudinal bars. So these are some important things, that only 2-legged closed stirrups should be there, and these should enclose the corner longitudinal bars, and this cross-sectional area should be calculated as like this, should be provided to resist the equivalent shear. And also code says that in addition to this condition, another condition which should be fulfilled is that in no case this ASV should be less than this tau VE, means equivalent nominal shear stress, minus tau SE into B into SV divided by 0.87 Fy. Here in this expression we have seen two new things, others you are aware of. B1 and D1. B1 is center to center distance between corner bars along the width, and D1 is center to center distance between corner bars along the depth. So these are the B1 and D1. Rest of these things in this expression you know. So you can move forward by putting values of these things whenever you are asked to design this thing. Now equivalent shear stress tau VE, that is coming in this expression here. This you will calculate as VE by BD. As we did earlier in earlier cases, we calculate it by dividing VU by BD. Here instead of VU we will be taking VE, equivalent shear force. Now, so this was about the taking care of that torsional movement or torque or twist in case adding it to the shear. Second thing is we have to modify our bending moment also if the torsional movement is coming into the picture in a structural member. And in this case we will calculate equivalent bending moment. So here effect of torsion will be combined with the bending, and an equivalent bending moment will be calculated for providing equivalent flexural longitudinal reinforcement. Earlier we were providing longitudinal reinforcement from flexure point of view. Here torsion is also added. So here we will be calling it as equivalent flexural longitudinal reinforcement. And this equivalent bending moment ME1 will be equal to MU plus MT. MU you know, that is given, or that is in normal cases the bending moment coming to the section. Here MT is calculated as TU into 1 plus D by B upon 1.7. This is given, this formula is given in the code. So MT you can calculate with this formula, and you can reach to the equivalent bending moment value here. Here if MT is greater than MU, then in that case longitudinal reinforcement shall be provided on flexural compression face for an equivalent moment of ME2, that is MT minus MU. Otherwise if MT is not greater than MU, means MU is less than or equal to MT, in that case this longitudinal reinforcement will not be provided on the flexural compression face. But if MT is greater than MU, in that case we have to provide this reinforcement for a value of MT minus MU. So that way we see that this torsional movement can be taken care of, torsional stresses can be taken care of by calculating the equivalent shear stress and equivalent bending moment. And for these modified values or the equivalent values of shear and bending moment, we can go for the design of the structural member as we have used to in our earlier cases. So that way means the effect of the torsion can be taken care of by modifying the value of shear force and the bending moment, and then we can go for the design of the structural member. Means no separate reinforcement is to be calculated, especially for the torsional movement. So this is all about its theory. So some problems are solved in your course material, so please go through that course material. If you face any problem, you can ask those queries in the next lecture, in which I will also try to solve some of the problems based on this theory. Thank you.